Yep.
More attention. So yeah, just to recall, just to recap, this week we are like in the classes also we have seen that we are focusing on some of the advanced topics in deep learning, and today we will be touching upon two such topics. and the first one out of them is adversarial robustness. So
Hello?
one thing that we have seen that like even though our classification models are very strong and powerful and we are able to generate images, neural networks can be fooled very easily, right? So and there
Hello?
deep learning world where we are still unable to do very well,
Hello?
right? So um, as and when these models are becoming parts of our lives, one thing that is seen is that there are attackers everywhere.
Yeah. So, starting with this week's lecture, we will cover pretty advanced topics in this week, and the topics are like self-supervised learning and adversarial robustness. So, so I'll start off with the self-supervised learning methods, and then we'll go to some of the adversarial robustness techniques. So, before going forward, uh, give me 1 second. I was just waiting for some people to join. Yeah. So before starting with the discussion today, we will first go into the details of different types of learning. So when you think of any machine learning paradigm, first thing that comes into my mind is that the supervised learning. So in the supervised learning setting, what we do is that we have a, let's say, we have a problem, and so we have a machine learning problem to learn, and we're given um, uh, uh, features and corresponding levels to learn from. So what we do is that we first train a machine learning model that will take in the feature and take in the levels and learn a connection and a pattern between these features and levels. So it sort of learns a relationship between a feature and a level. But when you so when you go forward, you can realize that features and levels are not always available. What I mean to say is that uh, what I mean to say is that when you work in a very real world setting, when you work in a very real world setting, it's not always practical to get all the labeled data. That means if you're working in let's say network industries, in network we you can get a lots of network packets daily by collecting network packets at your router, but uh, you cannot always label them. You cannot get labels for corresponding network packets, and you need human experts to label the data, and which is time consuming and costly as well. But if you think about unlabeled data, or the unorganized data, it's a lot. So you just go to the internet and you just search for anything, you'll get data in all format like text, video, images, audio, and whatnot. So the raw data is available, but the the label data is not. So then we came to the study of, then you come to the discussion of uh, unsupervised learning. So let's say like uh, we have a lot of data. We can learn the patterns in the data, and we can basically do all the unsupervised learning tasks, such as clustering or anomaly detection and all these things. But the question is, but the most important task are supervised learning tasks. The question is, can we learn a supervised learning task with data that have no level? That is, so I have a lot of data, they don't have levels. Some of the data have levels because it's very easy to label some of the data, some percentage of data. But I want to learn a supervised task using this unlabeled data. Okay. So there was a catch here. So how do you do that? So there was supervised learning, there was unsupervised learning, and there was something called self-supervised learning. The self-supervised learning is that when you are sorry, there's something called semi-supervised learning. The semi-supervised learning is that when you use the levels of some data to predict the level of some other data, and then you sort of iteratively do that and try to get levels of as many data set as you can. But that was not an efficient way of doing that. So that's why people invented this. That is called there's something called uh, self-supervised learning. So if you ask me a question, what's the self-supervised learning? I would say that it's a type of learning where the model exploits unlabeled data to learn meaningful patterns in a supervised fashion. So just see the term supervised fashion, not in an unsupervised way, or not in an k-nearest neighbors or k-means clustering. Those are unsupervised way, but the self-supervised learning is a type of learning where the model exploits the model exploit the unlabeled data to learn meaningful patterns in a supervised fashion. So just remember, we're learning in a supervised fashion. So you might ask, we have a lot of data. Let's say I have millions of images of different animals, and I want to learn a supervised task like, what is this animal? Like, is it a cat, or is it a dog, or is it a cow or something? So I want to learn that, but I don't have labels. I mean, I have labels, but for some of them, like 10 cats, I have labels for 10 cats, or like, let's say 100 cows, 150 dogs, but I have unlabeled data of like thousands of cats and dogs. So the thing that I can do is self-supervised learning. So here, how will you do that? Uh, so what it does is that it designs supervised tasks. Okay, so it designs supervised tasks from the unlabeled data to learn meaningful representations. So we have unlabeled data, and what it does is that it learned meaningful patterns by designing a supervised task out of this unlabeled data, and these tasks are called pretext tasks or auxiliary tasks. So this is not the task that we are looking for. Our target task is to classify different animals, right? But they, we can design some pretext task and auxiliary tasks that will not help us um, um, differentiating between cat and dog, or a few different animals, but it can certainly help us to learn the patterns of different animals. So Now, self-supervised learning is something you can say is that um, it's the way by which we learn some pretext tasks, which will eventually help us to learn our um, main task or the primary task. And to learn these pretext tasks, we do not need labels because we create them. Okay. So the question is why we need this self-supervision? Why do we need that? Uh, so the first reason is that supervised task requires a vast amount of level data, and getting level data is not always very easy. It's time consuming, it's resource consuming. You need people to level your data. It is also like expensive sometimes, people, because people need money. So if you go to Amazon mechanical trunk, so there are peoples which who are doing this masking job or like leveling job, doing a building box around the image or object for some few bucks. So you need to spend some money to if you want to get level data. So supervised tasks requires a vast amount of level data. So level data is expensive and we just have unlabeled data. So if you just go to the internet, you can get a huge amount of unlabeled data, which is for free. You don't need anything, just go and scrap all this data. So uh, so this is the mistype. So the question is how to exploit this unlabeled data. We have unlabeled data. We have a target task in our hand, but how to exploit this unlabeled data to reach our target task? The answer is by learning patterns hidden inside this unlabeled data by creating level tasks out of it. So we have unlabeled data and we have to create leveled task out of it. And once we create leveled task out of it, we can literally learn all the patterns of the data, and you can use this pattern to learn our target job. Okay. So starting with the first task in our hand, that's called image in painting. And as you can see, this is all about the self-supervised learning. I'll just give you one example. You will know, like, how to like how these things are designed. So the first is like SSL in CV, like that is self-supervised learning in computer vision. Example number one, that is image in painting. That says there's an image and we have a lot of image with us, like millions, but we don't have any levels with it. But we want to learn certain patterns of this image. Okay. So one way is to do is that this image in painting task. So what you do is that you cut a piece of image from anywhere inside the image, and your task is that to predict this part. So if the image, if this is the full image, if this is your feature and this is a level, so you converted a unlabeled data to a labeled data by sort of creating features and levels from this unlabeled data. So this now this you always have x and y in your supervised task. Now this x is divided, now you don't have any y, so now this x is divided to xx and xy. So this piece here is xy. Okay. So in image in pending, so you pass this initial part to the encoder. So this encoder encodes this image, and then you decode this to get a prediction. So the output decoder output size should be equal to the piece it was equal to the piece it was the piece that was taken out. So you sort of like uh, found a prediction for that piece. Then you have the actual piece with you because you just cut it out from the entire image. So you put that into perception, put that in place, and you took the L2 loss and the adversarial loss, and after training, the model will be able to paint what was there, what is missing inside an image. And this is called the context autoencoder. So the context autoencoder is trained to fill the missing part of an image, and the encoder is trained with a combination of L2 and adversarial loss. So we have a combination of L2 and adversarial loss that helps us like regaining this missing part in the image. And that is how, like, from a unleveled data, we create features and levels simultaneously. Okay. Another example, like we have here a piece of image where the middle part is cut out, and in the right is a human artist who tried to inpaint the image with his painting skills. And in the left hand corner, the reconstruction of the image by using only L2 loss, and in the D, figure D here, is a reconstruction of the image using L2 and the adversarial loss. This is a fairly good approximation of the true, fairly good approximation of the true pairs that is there, which is achieved by this paper. Okay. If you have a doubt, you can put it in the chat. So coming to the next task, that is the self-supervised learning in computer vision 2 is called the jigsaw puzzle. I'll get back to you in a moment. Okay, so give me a second, I'm just drinking water. Okay, so yeah, so second one is a jigsaw puzzle. So how this jigsaw puzzle work is that an object consists of different parts. So what this model learned is that it learned to uh, it learned that an object consists of different parts, and it also learns that spatial arrangements of different parts by solving a jigsaw puzzle. Okay, so there is a jigsaw puzzle, a jigsaw puzzle. So what we do is that we first take 9 cubes or 9 squares in an image. If it is color image, it will be cube. If it is a black and white image, it will be square. And then rearrange this 9 spots around the image. So that is your initial arrangement of the image. So this is the initial arrangement, and this is the B image. B is after shuffling the image. So now the task is that reshuffle the images, reshuffle the image to get the correct image back. Okay. So how do they do it? So they have a image. They have a they have a image, and each image is associated with an index, and each index is permuted. So certain percent of all the image is divided into 9 equal blocks, and these blocks are permuted according to the permutation corresponding to that image. So here's the image of a car, and this middle part is divided into 9 parts, and you reorder this image, reorder this patches according to the selected permutations, according to the selected permutations. So the permutation is 9, 4, 6, 8, 3, 2, 5, 1, 5, 7. This is 9, this is 4, this is 6, this is 8. So there will be 9, there will be 4, there will be 6, there will be 8. And yeah, so 1 to 9, and 9 is going first, then second is gonna be 6, 9, 6, sorry, 9, 4, then 6, then 8, and just like that. You have the permutations here. So all these permutations are now passed to different CNNs. So 9 tiles are shuffled via randomly chosen permutation from a predefined permutation set are fed to the network. So the task of this network, and these words are said, is to predict the permutation applied. So if the permutation is uh, um, this, so okay, so if each image is not an index, so I just mistakenly said it. So there is a permutation set, and each set have an index. So if this image is using this set, the prediction should be this one. That is, the output dimension would be 64 dimension, and in the 64 dimension, sorry, the output direction would be just one dimensional, and in that one dimensional, one number is to be predicted, and that should be 64. Okay, because 64 has this 9 to 6, 9 to 7, like this permutation that is given in the screen. So this algorithm predicts the index of the permutation applied, and output vector gives probability of permutation indices used. Okay, so let's say there are like thousands of permutations. The output layer will be 1,000, and in each iteration, it will give which permutation has the highest probability, and that will be the case. It doesn't have one layer at the end. It has like the number of layers in the end layer is equal to the number of permutation that is there uh, uh, in the permutation set. Okay, cool. So if you have like let's say 1,000 permutations, and this network will predict 1,000 probability corresponding to these 1,000 permutations, a cross entropy loss will be used for training. That is like, we'll use a cross entropy loss against this 1,000 predicted permutations and the 1,000 uh, not 1,000, the target one permutation, but represented as a one hot vector. Okay, see, so this was the case, and with this self-supervised learning task is over. So if you have any doubt in this setting of self-supervised learning, you can pause me and we can discuss a bit more about it, and or anything like self-supervised learning in general as well. I'll wait for 2 minutes for you to post the questions in the chat. Then we'll move to the next self-supervised task in hand. Okay. So coming to the third task in self-supervised learning, that is predicting the rotations in self-supervised learning. So to explain this, I'll use my lesson notes. This is week 12. Great. So uh, working. Let's say we have all these images, and this is a data set consisting of thousands of images, but no levels. We don't have any levels associated with this image. There is the image of a, let's say, person, there is the image of a cat, there is the image of a bird, and so on. But we don't have any levels associated with it. But we still, we're trying to learn a supervised task, like predicting the class of the animal here, a bird. So what you can do is that we can take the image, then so this is the image of a person. Then what you can do is that we can create a pretext task. A pretext task or an auxiliary task is a task that help us learn the patterns inside the image without actually learning the target task. So the benefit that we get from this type of learning is that we get to know the patterns of the image, even if we don't have any labels associated with the image. So what we'll do is that we'll do certain transformations to the image. It will like flip 90-degree, flip 180-degree, make it transparent. Let me see the transformations. Okay, so it's just 270 and 0-degree. Okay, so let's just stick to rotations. We can later add like cropping, then blurred, sharpening, anything. So when you rotate this image by 90-degree, it will be like this. 180, like this. 270, like this. 0, it will be like this. Okay, so what you have now is that from this one image, we have now created 4 images, and the level of this corresponding image is 90, it is 180, it is 270, and it is 0. So if you look clearly, if you look carefully, what you can see is that if we had, let's say, n images at first, now this n is converted to 4n images, because each image is now transformed into 4 times, and each of these 4 image maps to one of these 4 numbers, that is 0, 90, 180, and 270. Okay, so these are the uh, input features, and these are the levels now. So we will have 90-degree rotation of this image, and let's say um, the bird, it is a 0-degree rotation of the bird. There is a 270-degree rotation of cat. So the label corresponding to this feature would be 90, this feature would be 0, and this feature would be 270. Okay, so this G is taking X and Y equals to 0 and giving the X0, and similarly X1, X2, and X3. So these are all like rotated and transformed images, and each image have a associated label uh, along with it. So this label, so now we'll use a coordinate or any CNN model to predict these labels. Now this dataset is changed. The dataset is changed from just unlabeled image to uh, image with labels. So now we have a supervised task. We can use this to learn the pattern inside this image. And once we learn this, we'll have a structural representation of this image. So the neural network that will learn this image and rotation mapping will have all the in the initial layer with all the things to understand the structure of the image. Now once you have learned the structure of the image, you can remove this part of the network, and you can add another layer, fully connected layer, to this front part and retrain this model with the actual label data. So in this unlabeled data, it's not like that the entire data set is unlabeled, is that it's like very small portion of the data set has labels. Like if you have a picture of cat, there will be like 100, just 100 cat out of this million long data set, where you know this 100 images are cats. So now you can attach another block and create this entirely new block where you can use your image and actual levels, not the rotations, the levels, to retrain this image. You can freeze the initial layers because it is already trained with the pretext task. You can just learn this part and you will get a fairly good classifier out of it. Even if you have a very small amount of level data and millions of unlabeled data, you can leverage this millions of unlabeled data to learn patterns and learn connections between the image and the label without worrying much about it. So it learns high-level object concepts such as their location in the image and their type and their poses. So it's sort of, you can see there's a bird and it is getting rotated and it is passing it to a coordinate, and the objective is to predict 0-degree rotation, and it is to predict 90-degree rotation, and so on. Yeah, the levels I will be like 0, 1, 2, 3, because we don't really put the levels as cat or dogs. If we are predicting cats and dogs, we just put numbers correspond to that. That's why we have numbers correspond to each degree. Okay. So this is all the things that we are going to discuss about self-supervised learning this week. So if you have any questions, you can put it in the chat. Next we'll move to adversarial robustness. Okay. The adversarial robustness is a new topic, completely new topic than self-supervised learning. In self-supervised learning, we saw that how we how we used the unlabeled data to learn a meaningful patterns. But in adversarial robustness, we learn how tiny changes in the image can affect strongly the classifier's accuracy and stuff. So yeah. So in 2013 and 2014, two scientists simultaneously observed this one, is that they have an image and to which they add a tiny amount of noise, and this noise was so small that it was almost invisible to a human eye, that is very small. And they add this noise to the target image, and they add this noise to the image, and they get another image which they call an adversarial image. And when they pass these two images to the classifier, they got different predictions. So if you see in the left hand side, there's an image of a panda. There's an image of a panda. So the classifier is saying it is a panda with the confidence of 58%. It's saying that it is a panda. Then you add a noise, suddenly it's saying it's a gibbon with a confidence of 99.3%. And this noise is not random. So let me just be clear. This noise is not random. It's a well-crafted noise, and this crafted noise is added to this panda image to give price to this image in the right. And yes, this noise is added. It's not the same image. And this, after adding this noise, the confidence levels of the panda dropped, and the confidence level of given went so high, the model says it's a given. So uh, 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 just looking for the terminology, if I look for terminology, the image here in the left is called the input image, or the benign image, or you can say the um, um, original image, original image, original image. And this noise is called adversarial noise, and the resultant image is called adversarial image, adversarial example or image. Okay, so once people have started talking about this in image, so people and in from other domain try to imitate it. So people started like manipulating text. So if there is a original input, connoisseurs of Chinese films will be pleased to discover that Tian's meticulous talent has not withered during his enforced hiatus. Okay, and so this was a positive sentiment. This has a positive sentiment. So the adversarial image, so adversarial example in text says that you can either make the text visually similar to the original text, or you can make it semantically similar. That is, like changing the word connoisseur to annoisseur will make this sentiment negative by the um, sentiment analyzer. And similarly, if you look into the semantically similar word, like connoisseurs of Chinese footage instead of film, if you replace the word film with footage, um, so it is suddenly negative now. So it's the prediction given by the state-of-the-art neural network AI model is negative. Okay, so that's the adversarial attack on text. And there is also works on adversarial attacks on audio domain. That is, if you have, let's say, a ASR device. ASR is automatic speech recognition. So the way automatic speech recognition model work is that they have this ML model that takes in audio and convert it to text. So your devices such as smart home devices, Google devices, Alexa devices are runs on this idea that a automatic speech recognition model is running inside it. You pass text, you pass your voice as a command or a suggestion, or like a question. So it will just take this text. It will just take this input as a audio wave, and it will then convert this audio wave to text. So it will convert this audio waves to text, meaningful text, and from this meaningful text, it will try to understand what you're trying to ask. Then it will generate some appropriate response to it, and at the end, it will uh, output the uh, response that is needed. A way to fool this kind of model is that you play something, a human will hear something, and the model will transcribe it to completely different. Such as, if an adversarially modified yes will sound like yes to a human, but it will sound like no to um, the ASR model if we evade it. Okay. So this is like basic idea of adversarial robustness and adversarial attacks. So there is some basics of adversarial attacks. That is, first is the threat model. So let's say we're attacking a model that is let's say we're attacking a model, a machine learning model. um, by attacking, I mean we're crafting adversarial examples for this machine learning model. Okay, so we're crafting these adversarial examples for this machine learning model, and so sort of we're saying, let me see if I can craft an example. So let's say the target, let's make it more simple. Let's say the target model is a cat and dog classifier, and we're trying to find a cat and add some adversarial noise to it, such that the cat will still look like a cat, but it will be predicted as a dog. Okay, so you just understand the target task, right? The target task is, there is a cat and dog classifier, and it's performing at its best. Like, it's not like that it's a very weak model, or it's not like that it is a very a small model, like it's a very in the initial stage it can't discriminate between a cat and dog. It can. It has, let's say, 99% accuracy, or 95 to 100% accuracy. It can classify the every dog and cat that is there in this planet. That is case one. What you're trying to do is that we're trying to find a noise, let's say delta. This noise should have two properties. One is invisible to human eye. That is, if you add this noise to the image should look like exactly it was before to a human eye. Like a human can tell, okay, this is a cat. The second thing is that the model should be evaded. That is, the model should predict it wrong. That is, the model should say it's a dog. It's not a cat. It's a dog. So there is a fully trained good model with 95% accuracy. There is an image. You took that image. You get a noise. I'll not tell how to get a noise now. I'll discuss it later. But let's say you found a noise from somewhere, and you add this noise to the initial image, and you get an adversarial image, and that adversarial image is used. So then you pass the adversarial image to the model, and that model is telling that it's a cat, it's a dog, even if it's a clearly written, it's clearly visible that it's a cat. Okay, so coming back to the taxonomy, first, what's the white box attack? So you have a target model, right? If you have access to the model's parameter, if you have access to all the data distribution of uh, the data distribution of the training data with which it was trained, if you have the parameters, if you know the parameters of the model, which is very rarely to know, then that is called a white box attack. Like, you know everything about the target. That's a white box. I mean, you know everything about the target. Okay. The examples of these attacks are FGSM, PCD, and default. Okay. The second method is that the black box attacks. In the black box attacks, the attacker has no access to model's parameters, i.e., it's a different model or no model at all. So it to generate adversarial images. That is, the model, the attacker will not have any permission to see the model's parameter, the distribution from which the data came from, or the, I mean, which I mean, you obviously know which task this model is doing. Otherwise, who are you fooling? You have to know which task it is doing and how to fool it to do some other task, or do some wrong prediction. But you can never know about the parameters or the structure, architecture, and the distribution of the data with which it was trained. So that is called black box attack. And there is another middle ground, or you can say a point where you can access both of them. One is white box and one is black box, and third one is called the gray box attack, where you have some knowledge about the attacker's model, such as the input data distribution or the structure of the model, but you can never know the parameters, the optimized parameters it is using to make the prediction. Okay, cool. That's called the black box attack. So there is also taxonomy on the basis of objective. So uh, so let's say there's something called untargeted attack. So let's say you are adding some noise to the image, and and your goal is just to misclassify the image. Okay, you're not telling anything, you're just misclassifying the image. So you misclassify the image to something else, that is called untargeted attack. And then there is something that is called targeted attacks, when you misclassify it to something particular. Let's say you're classifying a group of animals into their respective class. Okay, there is cow, cat, dog, dove, blue jay, and human. Okay, right? So you aim to get the image classified as a specific target class different from the true class. Okay, so you want the cow should be identified as dog, the cat should be identified as man. It's not like that. You don't want the cat, you don't want to find a noise that will add to the cat, so that the classification output, the classification will be, the job will be misclassified, and the cat will be renamed as dogs. No, you want the cat to be classified as cow. You have to very specific targeted attack. That's called targeted attack, but the target is fixed. Okay, the aim is to get the image classified as a specified target class different from the true class, and you know the target class. That is called targeted attack. Okay, so it's 1 hour. Now we'll discuss two of the methods, first gradient sign method and the projected gradient descent method. So before discussing this part, we'll take a short 5 to 10 minutes break, and we'll meet after that. Okay, bye then. Okay, so we'll start with the idea of FGSM, the first gradient sign method. Let me take you to the uh, uh, live note screen where I'll describe about the FGSM algorithm in detail. Okay. Okay. So getting back to our discussion, FGSM. So understanding FGSM is much more. Yeah, sorry. Yeah. So understanding FGSM is much more important than understanding PZD because PZD is just an extension of FGSM. So let me start with discussing the FGSM. So let's say you have a neural network. This is a neural network, and okay, so this is a neural network, and you're passing any image to it and getting a prediction, and you have this W. Okay, so when you are training, what do you do? So what you do is that you pass the X to the network F, and you get and Y hat as output, and this is called the prediction. Okay, this is called the prediction. You have an actual Y, you have an actual Y, and mm, there's an actual Y, there's a predicted Y. So Then you'll calculate the loss y, and you'll back propagate this loss to update the weights, right? So if I just remind you about the backpropagation algorithm, it will be first step, you forward pass, that is f of x, calculate f of x. Second step is prediction, so f of x equals y. Then to y up y hat. Then calculate the loss. That is the loss of y hat and y. And step 3 is back propagate. That means you are taking the gradients of loss with respect to the W, okay? And the fourth is update the weights. Okay. Okay. This W new equals to old minus alpha times us is the learning rate. Okay, is the learning rate. So if you if you know about this plot, where you sort of plot between W and loss, okay? So in this plot, let's say you are initially here, then you draw the, then you take the gradient at this point, then you move in the opposite, the gradient is negative. So the gradient is negative. So you move it's negative, you move in the opposite direction of the gradient. So you move in this direction by a factor of alpha and you reach here. Then you move in this direction by a factor of alpha, you reach here, and so on. This is called the gradient descent algorithm. You're descending down in a gradient, descending down in the error curve, minimizing the error, and finally reaching a point where the error is optimal, not zero. The loss is optimal. This is the optimal loss point, and this is after the model gets trained, you will reach here. Okay, is the optimal loss point. But what happens? What if I tell you that this optimal point is it can be manipulated. So we are moving in the opposite direction of the gradient, and for you not to skip the global minima or the local minima, you want to take smaller steps and very carefully you update the weights, and so there's the final weight, and this weight optimal will be the final trend weights. Now what we're doing is that we will fix the weights because we don't have any access to the model. I mean, we have access to the model, but we can't change it. We change it like this, like, the loss depends on y and y hat, and y, this can be written equivalent to loss is uh, f of x y, right? So loss is dependent on x as well. So that implies you can take the gradient of loss with respect to x as well by fixing the weights. You can take the gradient of the loss with respect to x as well. X. Sorry, got muted in between. So since this loss also depends on x as well, we can take the gradient of loss with respect to the x as well. So that means we can represent loss with respect to x as well. So if we draw an error curve with error curve of x with respect to the loss, then the x is the input. It's fixed. It must be somewhere here or here. Okay. So what we do is that we sort of take. So let's say here is the point. We can take. So it's an effort to update the x. Okay. So we can take the gradient of this and we can move in the opposite direction of the gradient, and we'll reach at a point where the where the image. So now the weights are trend. We can do a very engaging session with the course instructor Vineeth that is just completed. Okay. Do you know? Yeah, I didn't know that because I just have a live session to continue, and I wasn't aware of any live session taken by Vineeth, Professor Vineeth, today. So also, like, I'm in a different time zone now, so I don't really uh I don't really have the messages coming forward. Like it's 12 a.m. at night, so I'm just getting live now. So I had this like I didn't know that. Okay. So there is this input X that is dependent on, okay, I see the all things are parallel going on. That's why it's very hard to attend some sessions. Yeah, last week I didn't take any session because the TA this was working with me was supposed to give me slides. He didn't give, so I couldn't take. I'll upload the recorded version of that. But yeah, so there are a couple of sessions going in parallel. It's not good. Like they should have mentioned that no session should go in parallel. At least one session per slot is good. But yeah, I think it's the last week, so it doesn't matter. Okay, so we sort of now saw that the loss is somehow related to the input X, and if we freeze the W, we can literally change the X as well. So we have the input image, we can change it. So what's the point of changing an input image? Because we don't want to change the input image, right? We just want the corresponding class for a given input image. So by changing the input image, what I mean is that if you go in the opposite direction of the gradient in the input image, it will be the classifier would be a better classifier. But these people did is that they moved in the direction of change. That is, they got the in the direction of gradient. So they got the slope from this point and they moved in the same direction. So what will happen? It will go away from the minimum. So the image will go away from the minima and the loss will increase. So if you go in this direction, the loss will have a huge increase. So the final image will be like this, X adversarial. So this is called the X adversarial. And this is the image X. So what I mean here is that you make a tiny change in the image towards in the direction of gradient, in the direction of gradient of loss. So you go towards the change, towards the direction of the gradient, it will increase the loss. So if you remember in gradient descent, if you go in the opposite direction of the gradient, it will minimize the loss. If you go in the direction of gradient, it will increase the loss. So that is X adversarial, and so since it is increasing the loss, it will increase the loss by rearranging the probability score of it, the probability score of the output layer, and this target probability score will change the level. Okay, so if you put that in a formula, it will be like your X adversarial equals to the X the original image X, then you go in the direction of the gradient, not the opposite. So you did a plus, and you take the sign of the gradient. So you take the gradient of the loss with respect to X, and the loss is between the X and Y true. Okay, so you take the gradient with respect to X of the loss, and you take the sign of it. The sign of it is like you take which sign is it has, like positive or negative. What is the sign of the slope? You take that, you move in the direction by what amount? Epsilon amount. So you move by epsilon amount, you get the X adversarial. So if you look into this image, it's an example of first gradient sign method of the FGSM. So this is the noise. So this noise is the sign of the gradient of the loss. The sign of, so you take the gradient of the loss with respect to X. That is, if I write it in a simple term, you're taking the derivative of loss with respect to the X. You'll get some value V. You take the sign of it. Is it a positive? It is the sign of it. Is it a positive? Is it a negative? You grab that. After grabbing that, you it is this. It is the sign of the gradient. This one. You multiply it with a small amount, epsilon, that is 0.007, which is very small. You multiply that, you'll get the adversarial noise. You add this adversarial noise to the image, you'll get the target image, and that is called the adversarial image. So in terms of targeted attack, so that is like this is the untargeted attack. You're just increasing the loss so that the distribution, the probability distribution in the output layer will somehow change and will make the panda to given. Okay, that is the untargeted attack. So there is something called targeted attack I discussed a few minutes ago. In targeted attack, the so what we do is that we try to maximize the loss. So we try to minimize the loss in the target class. So in targeted attack, in untargeted, we just want the image to be misclassified to something else. But in targeted, we want it to misclassify to a particular class, not to something else random, but to a particular class. So in this case, we're saying that we want a targeted attack, and so to do that, what we'll do is that we'll modify the image in such a way that it will maximize the target class, minimize the target class loss. In the first case, it was maximizing the initial class loss. Here it is minimizing the target class loss. Since it is minimizing, you just have to go in the opposite direction of the gradient, and you need to take the gradient with respect to the target class, not to the initial class. So this is all about the first gradient sign method. So PGD, or the projected gradient descent, is just an extension of this FGSM. So this FGSM said is that FGSM said is that FGSM said is we have a curve here. So we have x, we have loss here. Let's say the initial value of x is here. So it says that you take a gradient, you just move in the opposite direction of the gradient, and where you reach that point is the x adversarial. Okay. But what PGD says is that, and this movement should be very small, such as 0.007. But what PGD says is that PGT, what it says is that, so let's say this is a box and here is the original image x. So you first move in this direction. So this is the resultant direction that you are moving. So each dimension of x will have a sign, right? So I represented it as a 2D, but there will be a lot of dimension of x. Each dimension will have a sign. So the resultant direction the x will move is the resultant direction of all these signs. So let's say we're moving in this direction by a small amount. So you are here. Now this is the x updated. This is the x1. Okay. This is the x1. Now, for the second time, you will again apply all these things, and you will again go in the direction of the gradient, but you'll go like this. Let's say you went like this. Now you are out of this epsilon box, right? So when you're out of the epsilon box, you'll project yourself back perpendicularly to the box. Okay, so you'll be here. So this will be your x2. So like you're projecting yourself back. Then you are again moving, reaching here. That is the x3. Then you are again moving like this, let's say here. Now you have to project yourself back to the box, no, perpendicular to the box. Yeah, this direction. And similarly, like whenever you go out, just perpendicularly go back to your box. You go out, go back to your box like that. You go here, you go out, go back to your box. So it's like you're sort of moving away from the local minima and increasing your loss. But every time you do it, you're just checking that are you out of your mind? Like, are you out of the box, epsilon box? If you are, just project it back. So if you see the formula here, complete method, unlike FGSM, it takes steps till the point it has found an adversarial example. Earlier in the FGSM, it will just take one step. If there is no adversarial example, it will just skip it. Say there is no adversarial example. But here, it'll go until you find the adversarial example. There is no constraint on time. You can just search for an entire time. You're allowed to search for it. When the perturbation goes beyond the bound, the point is projected back into the designated neighborhood. That is, the x zero adversarial equals to x. The x t plus one adversarial equal to projection of xt plus adversarial plus epsilon of sine the gradient of loss with respect to x adversarial and true. So this is a setting where the projected gradient descent really work, and this is the way we represent all these things. So today we are reaching at the end of this discussion, and this is the end of the week 12, and we will soon carry out a extra session which will contain all the summarization of all the things that was there, and it will summarize all the discussions, and I might go on to some special topics and discuss them in this week. I think it's on October 20th or 19th. I'm not sure. Yep. So till then, stay tuned, and we will try to like wrap this up in a big way. Thank you everyone who joined, and I'll see you next week, next session.